Professor G.L. Shiv Kumar Babu will be chairing this particular session of the 39th IGS annual lecture.
It's a pleasure to introduce the IGS annual lecturer, Professor Viladkar, Department of Civil Engineering, IIT Roorkee. He joined the Department of Roorkee as lecturer in Civil Engineering in 1978 and obtained his PhD in 1984. And in 1996, he became a full professor. His research interests include dynamic solid structure interaction, rock mechanics, rock engineering. He published several papers. He guided 17 PhDs and about 73 master's theses. He worked as United UNESCO Fellow in Italy, visiting professor in the University of Wales, Swansea, then a technical University Budapest. He has been an active consultant. He has been a member of the Research Council of CBRI and many other technical committees. He has received several awards, such as the Outstanding Contribution to Rock Mechanics Award by the ISSRMT, and also the Lifetime Achievement Award in Rock Mechanics, and Honorary Fellowship, and many other contributions. I would like to request Professor Viladkar to give his IGS annual lecture. Thank you.
Good morning to one and all present here in the audience. Honorable Chair and President of the Indian Geomechanical Society, Professor Shiv Kumar Babu. Honorable Co-Chair, he is not present here, Professor Shahu. Senior professors present here in the audience, including Professor Ramurthy, Professor Madhav, and then we have Professor Shiv also present here. Distinguished delegates from within India and abroad, young geotechnical engineers, members of the organizing committee of this IGC 2017, friends, ladies and gentlemen. This is my maiden visit to IIT Guwahati, and it gives me tremendous pleasure to be here in the lush green sprawling campus of this institute, which has been ranked by the Ministry of Human Resource Development in New Delhi as the 5th cleanest government institution in the Swachhata rankings in the country. At the outset, I must greatly appreciate this honor of having been invited by the IGS to deliver this prestigious 39th annual lecture during the proceedings of this conference IGC 2017. I am happy to inform the audience that this is the 8th time that Roorkee has been granted this honor. I personally treat this honor as more of a tribute to my many senior professors in the Department of Civil Engineering in the erstwhile University of Roorkee, and my present colleagues in the Geotechnical Engineering, Structural Engineering and other groups of the Department of Civil Engineering in IIT Roorkee, because I had an opportunity to closely work and interact with many of them. I treat this as an honor even to my MTech students as well as PhD scholars who used to work day and night tirelessly to implement the ideas which I try to float before them. I am also extremely thankful to the Indian Geotechnical Society, the organizers of the IGC 2017, especially Professor Murali Krishna and his entire team, to Professor Diganta Goswami, who is the chairman of the IGS Guwahati chapter, for giving me this unique and wonderful opportunity to deliver this IGS annual lecture. With these few words, friends, I would like to now come to the main theme of my lecture, which is geomechanical challenges practices and innovations. This lecture is based on basically the industry-institute interaction. I have tried to avoid all the mathematics, and I will be concentrating more on the physical aspects of the problem. And my intention is to encourage the young geotechnical engineers who have their entire career before them. I hope I succeed in my effort. So to start with, let me take up the applications of geotechnology. Usually include 4 different aspects. The first one is site characterization, which includes field exploration and laboratory testing. Then comes the design aspect, which involves interpretation and evaluation of the field and the laboratory test data, application of various theories of ground mass behavior, application of the concepts of ground structure interaction, and also the groundwater flow. The third aspect is that of construction. The main aspect includes adjusting the design and construction methods so as to accommodate the actual ground conditions. The last aspect is the performance assessment of the structure during the construction period as well as in the post-construction period to account for the great variability of the ground and to validate the designs by monitoring the actual field performance. When I look back, I find that the developments in the theory of soil mechanics started way back in 1978 in the 18th century when Coulomb presented his famous wave theory of earth pressure. Incidentally, he was also the first person to propose that the shearing resistance of the soils is a function of both interparticle cohesion as well as interparticle friction. Almost 80 years later, in the 19th century, we had 3 main contributions in the form of the famous Darcy's law, the Stokes law, and the Rankine's theory of earth pressure as well as bearing capacity of foundations. When you come to the 20th century, in the first half part, we had major contributions coming from people like Casagrande, Fellenius, Professor Carl Terzaghi, and so on. And all the basic developments in soil mechanics, including the stresses in soils, the consolidation of soils, the shear characteristics of soil, the earth pressure theories, etc. All these basic theories were developed, and as such, all these topics, they form various chapters of the famous text written by Professor Donald Taylor way back in 1948. It came out to be a classical text. But when you come to the second half of the 20th century, the developments have been really great and fantastic. Especially during the decade from 1960 to 1970, we had 3 new subjects introduced in this area: the rock mechanics, soil dynamics, and the finite element method, and with that, applications of numerical methods in the field of geotechnical engineering. We were also introduced to the concept of soil structure interaction and the liquefaction of soils, and a lot of work was initiated in the area of offshore geotechnical engineering. In the following decade from 1970 to 1980, we had a lot of contributions coming in the fields of expansive soils, constitutive modeling of geological materials like soils, rocks, and rock masses, various in situ testing methods, the technique of centrifuge testing of geostructures under high in situ stress conditions was also introduced during this decade, and the whole field of geotechnical earthquake engineering was also opened up during this decade. In the next decade from 1980 to 1990, we had introduction to environmental geotechnics, the ground improvement techniques, and also the concepts of risk as well as reliability introduced in geotechnical engineering. During the last decade of the previous century, we had a lot of contributions in the area of land reclamation, the waste containment, site remediation, seismic risk reduction, apart from, of course, the applications of geophysics as well as the geographical information systems in the field of geotechnical engineering. In fact, this particular field of soil mechanics came to be known as soil mechanics and foundations engineering during the first half of the century, and in the year 1970, the area was retitled as geotechnical engineering. Despite so many developments having taken place during the second half of the previous century, there still remains a major problem and a concern that the state of practice in geotechnical engineering does not really match so much with the state of art which has already been developed. And it is not that I am saying this. This has been the opinion of many of the experts abroad. They say that even when the knowledge exists, either economics or ignorance or the lack of time leads to harmful and at times somewhat dangerous practices. Well, with this remark, I would like to now come to the main 3 case studies which I am going to very briefly discuss here, just to give idea to the young geotechnical engineers as to what are the various challenges before them, how unconventional conditions you have to face. And I am going to consider here the cases of 3 extreme loading conditions, including the impact, penetration and the blast loading due to the hitting of a missile on an underground structure. The second is the difficult aspect of tunneling in the squeezing ground conditions in the lower Himalaya. And the third one is, of course, the soil structure interaction of the large industrial cooling towers under extreme wind loading conditions. Coming to the first case study involving the investigation of an underground technical facility under a missile attack. Those who are not conversant with the blast loading because it is unconventional, let me inform that there is no specific guideline or the Indian Standard Code of Practice as regards the impact and the blast resistant design of structures is concerned. Probably because the probability of occurrence of such loads is extremely low. This particular plot shows the typical characteristic of the blast loading, wherein we find that following the blast, there is instantaneous development of the peak blast pressure, which is then, it decays with time subsequently, and also includes the negative pressure. When I say this overpressure, it is always in excess of the atmospheric pressure. The entire phenomenon of this blast loading and unloading takes place almost instantaneously and finishes within a matter of few milliseconds. So therefore, in this short time duration of few milliseconds, you have very high strain rates which are mobilized in the geological materials or structural materials. And therefore, when you try to attempt such problems, you need to involve the constitutive modeling of soils, rock, concrete and rock masses, which are functions of extremely high strain rates as well as the temperature that is mobilized following the blast. When a missile hits a target, the objective of the missile is to penetrate the target up to the maximum possible depth inside the target before it undergoes explosion. The ballistic resistance of any target for that matter is a function therefore of these 4 parameters: the ratio of the projectile diameter to the projectile thickness or the stiffness of the target, the angle of incidence of the projectile, the mass of the projectile and the shape of its nose. When a high velocity missile impacts the target, it leads to 3 major phenomena. The first one is the spalling of the concrete, which leads to a crater formation. Then the perforation of the target, because the missile has a tendency to penetrate through and through the target. And then the third one is the scabbing, which occurs on the rear face of the target, and usually the area which is associated with scabbing is much larger than the area associated with spalling. The net effect of the blast load, it depends on the geometry of the structure or the stiffness of the structure and the position of the structure in relation to the source of explosion. I am considering here a typical case of about a 900-meter long tunnel with its portal end P1 here and a portal end P3 there. This tunnel is just an approach tunnel to a large underground technical facility, including multiple caverns and interconnected tunnel network. This profile shows the profile of the rock cover, and as you see here at the portal end P1 as well as at the portal end P3, the amount of cover is extremely low. At P1 end it is just about 2 meters, and at the P3 end it is just about 6.5 meters. This tunnel passes through geological formation which includes by and large amphibolite schist but of varying quality. It is the quality varies from good rock to fair rock to poor rock and to also very poor rock, except for a small stretch here of the tunnel which passes through either dolerite or arthroporzite. And then you can see here the corresponding values of RMR which are very low at both ends of the approach tunnel. The primary issue in this aspect was the safety of the tunnel near the portals P1 and P3. The initial 130 meter stretch of this particular tunnel from P1 end and about 90 meter stretch from the P3 end, they were supposed to be constructed by the cut and cover method of construction, whereas the remaining tunnel was to be constructed by following the conventional drill and blast method. The problem is that in the extreme event of an incoming missile directly hitting this cut and cover portion of the tunnel, the entire technical facility was supposed to be left inaccessible and redundant. And the client imposed a constraint that while working out a solution, you cannot change the surface topography or the surface profile. So therefore, along with the engineers from the client agency and we people try to work out different solutions. And what I am considering here is just one final solution which was finally implemented into the field. And because it's a major impact of a missile and it was not affordable to that the approach tunnel undergoes any damage, we decided that this main tunnel, which has got a lining of about 1.2 meter thickness, will be enclosed or enveloped in another tunnel which is called as a burster tunnel. The thickness of the RC lining of this main tunnel is 1.2 meters, the thickness of the burster tunnel is also 1.2 meters, and 3 meter gap between the two tunnels was to be compacted, was to be filled by compacting sand into it. And above this burster layer, you have about just a 2 meter thick rock cover, which is basically amphibolite schist. That's the type of the projectile which was supposed to hit the approach tunnel. The length of the missile is about 1.348 meters, the diameter is about 0.48 meters. The mass of the projectile is about 462 kg, but the mass of the actual explosive charge inside the missile is about 300 kg. And the impact velocity was considered as 200 meters per second, equivalent to about 720 kilometers per hour. This is the assembly of the approach tunnel near the P1 end. The entire width of the assembly, including both the tunnels, the sand layer and the overburden, is roughly about 24.8 meters, and this in this direction is 20.8 meters. And we had to actually work out a three-dimensional dynamic analysis subject of this entire assembly subjected to impact and blast loading. So as a first step, we try to consider only the response of the curved burster slab alone, without main tunnel, without the sand layer, without the overburden, just purely a curved burster slab or the burster tunnel with a 1.2 meter thick concrete, both with reinforcement as well as without reinforcement. Reason why we consider the two cases are, you can realize from this particular table that when we try to consider the burster tunnel without reinforcement, we got a spalling on the outer face of about 2.5 meter diameter and the scabbing of about 2.5 meters on the inner face, and the penetration of the missile inside the burster tunnel was of the order of about 0.63 meters. Whereas when we consider the reinforced tunnel, then we find that the spalling diameter has increased, the scabbing diameter has significantly increased, but the penetration has reduced. So for considering this, we had to consider the fracture behavior of concrete using the ductile damage plasticity model. But when we try to now understand the response of the complete assembly to missile impact as well as penetration, you can see here, this is the longitudinal section of the entire assembly along the length. That's 2 meter thick rock cover, that's 1.2 meter thick buster layer, this is 3 meter thick sand layer, and that's 1.2 meter thick main tunnel. And if I concentrate on this area where the missile has hit the tunnel, then I find here in the blown up view that the missile has penetrated into the overburden up to a depth of about 1.84 meters, but then it has not touched the buster layer. So you still have a gap of about 15 centimeters between the tip of the missile and the outer surface of the buster layer. This is the picture as far as the compression damage is concerned, but if I consider the tension damage, then I find that here on the inner face of the buster tunnel, you can see here in the blown up view, this red portion, this is all tensile damage on the inner surface of the buster tunnel, but I was happy to see to it that the missile does not penetrate into the buster tunnel. So therefore, when we try to compare the two situations where you have got the buster tunnel alone and you have got a complete tunnel assembly, then I find that because of the very low stiffness of the overburden material, which is in the form of virtually fragmented rock, you have a penetration into the overburden of about 1.84 meters as against a penetration of about 0.63 meters in case of buster tunnel without reinforcement or 0.33 meters in case of buster tunnel with reinforcement. And then when the missile comes to rest in the overburden after its penetration, it explodes. Now when it explodes, you have a situation something like this. You have a buried structure and the missile can directly hit onto the buried structure, and that's the distance r of the buried structure from the source of explosion, which is the mass center of the explosive charge. In case the missile hits in the near vicinity, then that's the distance r, and this distance r is actually extremely important because the peak blast pressure that is mobilized after the explosion is a function of this distance r as well as the mass of the explosive charge. So also your peak particle velocity or the peak acceleration, they are also the functions of this distance r and the mass of the explosive charge. And then this peak blast pressure, it reduces with time in an exponential manner and then decays it to a zero pressure. The whole phenomenon occurring in a split of a second or in few milliseconds. So when I try to analyze the entire assembly to this additional explosion loading, then I find that corresponding to a penetration of about 1.84 meters of missile into the overburden, the distance to the explosion was worked out as 5.2 meters from the main tunnel, and the explosive charge is 300 kg, and I find that the maximum blast pressure that is exerted is about 5.55 megapascals. Now, when the whole assembly was analyzed for this blast pressure, these are the plots, not very clear here, but corresponding to different stages of deformations, and that's the plot corresponding plot of the normal stresses corresponding to the final stage of deformation. And then we found that in the side wall of the main tunnel, that's the main tunnel actually, this is the 1.2 meter thick main tunnel followed by 3 meter thick sand layer, followed by 1.2 meter thick buster layer, followed by 2 meter of overburden. So in the side wall of the tunnel, I find a high stress concentration, and this is of the order, the maximum compressive principal stress is of the order of about 28 megapascals, but it is all compressive, and it was thought that the tunnel can successfully withstand the stresses without any damage. So the main tunnel remains undamaged. When we try to analyze the situation at the other end of the tunnel, that is P3 end, where the rock cover is about 6.5 meters, these plots show the distribution of the maximum principal stress in the entire assembly, and this is corresponding to the final stage of deformation, and we found that the maximum principal compressive stress in the main tunnel is only of the order of about 14.76 megapascals, because the blast pressure in this case had reduced. If I go back to the table, in case when the overburden is about 6.5 meters, we found that the missile penetrates into the overburden up to a depth of about 4.8 meters, the charge remaining the same the distance has of the source of explosion has increased, and I find that the blast pressure has reduced to about 4.48 megapascals. So corresponding to this blast load, we find that in this case, the maximum principal compressive stress mobilizing the side walls of the main tunnel is only about 14.76 megapascals. The entire design was carried out on basis of this particular analysis, and the suggested design was actually implemented in the field, and the entire technical facility is presently fully operational. Then I come to the second case. I have chosen 3 different problems because not at all the engineers present here are from the same background. So therefore now this is a case study from the area of rock mechanics and rock engineering. It's a case of a headrest tunnel of the Kishan Ganga hydropower project constructed in the state of Jammu and Kashmir, just near to the line of actual control. This project is still a matter of discussion as well as controversy at the International Court of Justice in The Hague, Netherlands. India won the case twice, but it is still under discussion. This project includes about 37-meter high concrete face rockfill dam, along with a spillway and intake structure, and added to the headrest tunnel in the famous Gurez Valley in the state of Jammu and Kashmir. This is highly terrorist infected area. So in this Gurez Valley, we had this entire dam and the appending structures constructed. The headrest tunnel starts in this area. It's about 24-kilometer long headrest tunnel with a diameter of about 6.3 meters. Ends up in the Bandipora district of the state of Jammu and Kashmir, at a location where you have an underground powerhouse, and this 24-kilometer stretch of the HRT helps us to achieve a head of about 700 meters between the reservoir and the underground powerhouse. That shows the topography of the project area. Somehow the colors here are not very clear here, but this is the location of the dam in the Gurez Valley, and that's the alignment of the headrest tunnel, which is 24 kilometers long. And here in Bandipora, you have an underground powerhouse to generate about 330 megawatts of power. Now, this particular 24-kilometer long headrest tunnel passes through 6 different geological formations, each having its own characteristics. And the first formation, in fact, at the dam end as well as at the powerhouse end, the tunnel passes through what we call as Panjal volcanics. These are typical Panjal volcanics exposed at the diversion tunnel outlet, followed by a Rajdan formation, which is comprised of moderately massive siltstones, followed by a Hastoji formation, which is relatively a very big formation comprised of thinly foliated metasiltstones. And this photograph shows extremely high weathering at the surface. This Hastoji formation is followed by a Hafkalan formation, again comprised of metasiltstones, but showing excessive weathering at the surface. This is followed by a Trackal formation, comprised of highly weathered metasiltstones, which are moderately massive and well foliated at places. And then this table shows that if you have a look at the strength, the rock mass compressive strength for Panjal volcanics and the Trackal formation is quite high, of the order of about 65 megapascals, 31 megapascals. But in these 3 geological formations, the Rajdan formation, the Hastoji formation, and the Hafkalan formation, the rock mass compressive strength in case of Rajdan is just about 1/10, and that's extremely low compressive strength. These are the values of the RMR, range of values of RMR observed. The maximum incidence stress along the stretch of the HRT at a distance of about 20.5 kilometers is of the order of about 24 megapascals, and the minimum incidence stress at the Bandipora end of the tunnel is about 1.8 or 1.9 megapascals. The primary issue was the designers of the project were foreigners from London, and the construction agency was from within India. The designers did not have the experience of working in the Himalayan terrain, and the construction agency also was relatively new to the Himalayan terrain, and therefore, the designers had recommended the excavation of the entire 24-kilometer stretch of the HRD using the tunnel boring machine. So therefore, the shield of this tunnel boring machine was designed to withstand a pressure of about just 1 megapascal. It was being designed and manufactured in Germany and procured at a cost of about 350 crores. And this TBM, the question was that if the TBM shield is designed to withstand a pressure of just 1 megapascal, in view of the very poor geological formations, particularly the Rajdan, the Haskoji and the Haflan formations, what will be the extent of the convergence of the tunnel upon excavation, how much pressure it would exert on the TBM shield, and whether TBM shield would be able to withstand that pressure or not. The pressure exceeds 1 megapascal, then it was expected that the TBM shield will get totally jammed. The TBM will neither be able to move in the forward direction, nor it will be able to move in the backward direction. And therefore, the simple question now was whether the TBM technology in this case would be successful at all or not. Now, to handle this problem, we first tried to make use of the approach by Singh and Goel of 2006 to work out the various ground conditions through which the tunnel is possible. And we found that in this stretch of the tunnel from 9.5 kilometers to 14.5 kilometers, which is in the Rajdan formation, there are only mild squeezing conditions, but the entire Haskoji formation will experience very high squeezing ground conditions, whereas the Haflan formation will have practically non-squeezing conditions. The Panjal volcanics were practically self-supporting that. But then to get doubly sure, we tried to make use of the approach by Prof and Morenash, which was presented in the year 2000. It classifies the degree of squeezing during excavation on basis of the percentage tunnel closure or the normalized tunnel closure. You find that corresponding to 1 to 2% of tunnel closure, it's a very mild squeezing ground condition, but when the closure exceeds about 7%, you get a very high squeezing ground condition. Along with this, along with the prediction of the ground condition, we also try to predict the convergence of the tunnel that will occur upon excavation, and also the likely pressure that will occur in the side walls of the tunnel. And then we found that the pressures that are exerted would range from as low as 4 to almost 48 megapascals, and you will have these different conditions during tunneling of the moderate squeezing condition, the high squeezing condition, very high squeezing condition in the Rajdan formation, again very high squeezing condition in the Haskoji formation, very high squeezing condition again in the Haflan formation. Now this actually raised an alarm, and therefore we try to predict what will be the standard time. That is the time or the amount of time for which the excavated tunnel can be left unsupported. And then we found, so therefore this standard time was evaluated on basis of our own work for evaluating the standard time as a function of the rock mass rating, the depth of overburden and the size of excavation. And then we found horribly that in these three formations, the standard time is as low as few hours. The maximum standard time was observed as about 1.25 days, otherwise it is in hours. Now if you try to take into account the sequence of installation of the support system, we were informed that the concrete liners would be installed within 8 hours after excavation of the tunnel. The pea gravels would be filled up, pea gravels would be used to fill up the space between the excavated periphery and the TBM shield. And it will take about 28 hours. So the total amount of time required for support installation is almost 36 hours, whereas we found that in these three formations, the standard time is extremely low. So it was well known that you will have face problems during tunneling. So our first recommendation was the pre-excavation grouting of the rock mass ahead of the face of the tunnel before the TBM advances. And with this pre-excavation grouting of the rock mass ahead of the tunnel face, we expected an improvement in the rock mass rating of about 25, and therefore we tried to modify the rock mass rating and we tried to rework the ground conditions and the stand-up time, and then we found that It has helped us improving the stand-up time in this stage, but in this particular stage from 10 kilometers to about 15 kilometers, it is still very small in the range of 1 to 20 hours, and in the entire Hasturi formation, it's awfully low. So therefore, we gave a second recommendation to carry out the primary grouting of the P-gravels in the space between the excavated periphery and the TBM shield. And this primary grouting was supposed to be finished within 6 hours. So corresponding to this now, when you try to carry out this grouting, you are trying to create a stiff ring around the periphery of the tunnel, which should improve the performance, and therefore we try to work out both the tunnel closure as well as the support pressures using these expressions for support pressure developed for the lower Himalayas as well as the tunnel closure. And then we found that in the Hasturi formation, the support pressures are far exceeding the design pressure of the TBM shield, whereas in the rest of the length of the entire HRT, the pressures were less than 1 MPa, but in the Hasturi formation, which was problematic, the anticipated support pressure was more than 3 times the design pressure. So therefore, we gave a third recommendation. In order to reduce the convergence of the rock mass, we suggested to go for secondary radial grouting of the rock mass surrounding the tunnel, both in the tunnel stretches, wherever they were expecting or anticipating the moderate or the high spacing ground conditions. And this was to be completed within 20 days after the primary grouting. The extent of this radial grouting was almost equal to the thickness of the broken zone developed along the periphery of the tunnel. This was also predicted from the analysis. And then we found that even in Hasturi formation now, with the secondary radial grouting, the pressures on the TBM shield work out to much less than the design pressure of 1 megapascal. These recommendations were actually implemented during the tunneling using TBM technique, and I'm happy to inform you that the tunneling was completed in time without any problem. Then the third case is again for those by and large who are from the industry here, including the phenomenon of soil structure interaction of the industrial cooling towers under extreme wind loading conditions. In view of the fact that this was in fact at a time when the Kakrapar atomic power plant was supposed to be constructed, in view of the fact that so many failures had occurred in Britain, in France and other places, almost about 5 major failures. This is a very old photograph of the Ferry Bridge tower collapse in United Kingdom during extreme wind condition. And you can see here out in a battery of about 8 cooling towers, 3 towers have totally disappeared during the cyclonic conditions. These extreme wind loading conditions are extremely unsymmetrical. The Reynolds number, which is corresponding to this situation, is extremely high, of the order of about 2 into 10 to the power 5. And then you have tremendous turbulence generated around the periphery of such cooling towers. This is a typical photograph of the Kakrapar atomic power plant in Gujarat. And we had an opportunity to analyze these towers under extreme loading conditions, considering the phenomenon of soil structure interaction, and that's where the role of geotechnical engineers comes into picture. These towers are about 115 meters high, with a base diameter of about 104 meters, the diameter at the throat level of about 50 meters, and the diameter at the top of about 54 meters. The entire tower shell is supported on, in fact, this is not visible here, on A-frame columns, or columns of the shape of A-frames, which are about 0.7 meters in diameter and about 7 meters in height. And the whole assembly is supported by an annular raft, almost 106 meters in diameter, 94 outside diameter, and 94 meters inside diameter, about 5 meters thick, laid at a depth of 5 meters below the ground surface. And that's the type of soil strata below the foundation. You have 2 meter thick stiff silty clay, displaying the SPT N value of about 31, a 4 meter thick dense sand strata with the SPT N value of about 70, followed by 10 meter thick weathered and fragmented rock, giving the SPT value of about 100. If you have a look at the Indian Standard Code of Practice, especially from the point of estimation of the pressure that is exerted on the tower, it suggests a symmetrical wind pressure distribution which is expressed with the help of such a Fourier cosine series. But when you consider the cyclonic conditions, we expected that the pressures will not be symmetrical. Because of high turbulence, you anticipate unsymmetrical wind loading conditions, and therefore we try to go in for the actual wind tunnel testing of on a model of the cooling tower, which was designed on principles of similitude, a geometrically similar model on a scale of about 1:400. And while modeling in the wind tunnel, we also tried to consider the effect of the surrounding structures in the close vicinity of the tower in the overall plant layout. The testing was carried out under the gradient wind conditions corresponding to a zonal speed of about 160 kilometers per hour. The corresponding value of Reynolds number is about 2.66 10 to the power 5, and then we try to estimate on basis of the wind tunnel testing these pressure coefficients, which are actually the pressure at any point on the surface of the tower in relation to the pressure that is exerted at the throat level of the tower. And these pressure, you can see here the profiles of the nature of the wind pressure profiles all around the periphery of the tower and at different elevations along the height of the tower. We have the profile corresponding to the throat level, where the diameter is minimal. At the top of the tower, at about 40 meters below the throat level, at about 80 meters below the throat level, and all these pressures are actually unsymmetrical, and it actually gives the values of the pressure coefficients, and these pressure coefficients can also be expressed. Now, when we try to define this with the help of a mathematical expression, we had to use a full Fourier sine cosine series with almost 7 harmonics, and then these pressure coefficients can be converted into the actual pressure at any height along the tower through what we call as the design wind pressure, which is a function of the design wind speed, which in turn is a function of the basic wind speed corresponding to about wind velocity of 150 or 160 kilometers per hour for a written period of almost 50 years. Forget the analysis part because it was an intricate analysis involving the shell structure, the column, A-frame column assembly, the annular raft, and the soil mass. We had to use the special shell elements for disguising the tower called as the semi-roof shell elements. But when I come to the response of the tower for the actual unsymmetrical wind loading, which was estimated from the wind tunnel testing, we found that the maxima of the radial displacement is very close to the throat of the tower, as against the maximum of radial displacement which occurs very close to the base of the tower when the wind pressure around the tower periphery is symmetrical. For a symmetrical wind pressure distribution, we found that the maximum displacement is just of the order of about 40 or odd mm, but in the unsymmetrical wind loading condition, the cyclonic conditions corresponding to a speed of about 160 kilometers per hour, we found that the maximum displacement near the throat of the tower is exceeding even half a meter. So that again there is an alarm, and the entire design had to be revised. We also tried to plot the profiles of total settlement, differential settlement. We observed a differential settlement very close to about 25 millimeters and a typical contact pressure distribution below a 5 meter thick raft, which is still behaving as a flexible raft. So we concluded from this study, and this is in the interest of the all those who have come from the industry, that in a situation where you have a battery of towers in an overall plant layout, you may have a battery of towers in a thermal power plant or a nuclear power plant. There are many structures in the vicinity of the plant. For the cyclonic conditions, it is best to go in for the actual wind tunnel testing and predict the wind pressure distribution profile all around the periphery of the tower as well as along the height of the tower. These unsymmetrical wind pressure conditions, they totally alter the deformation pattern of the entire tower and the assembly with the foundation system. the maxima occurs very near to the throat level as against the case of the symmetrical wind pressure distribution. And the entire, because of the, what we call the change in the deformation, entire deformation pattern of the tower, because of the differential settlement which comes into picture, there is a total change in the hook forces and moments in the tower, the meridional forces and moments in the tower, changes of forces and axial forces, shear forces and bending moments in the A-frame columns. And therefore, it is advisable that in such situations, one should go for the prediction of the actual wind pressure distribution, then carry out the soil structure interaction analysis, and then modify your designs accordingly or confirm your designs for the safety. Well, that finishes the 3 case studies, and this is the last part of my lecture, wherein I will try to project very few geomechanical challenges for the young geotechnical engineers who are attending here this conference, and for those also who have not been able to participate. You all know very well, because this is an anticipation for the entire 21st century and maybe also beyond. You all know that the overall economy of any country is basically governed by the energy sector. It's a large chunk of the national economy, and what has been found is that the existing energy sources are fast depleting. Easy to explore sources have already been explored, and the difficult to explore energy sources, they require tremendous knowledge of geotechnical engineering and also the related areas. The future energy sources, as a part of discovery and recovery of these resources, have been predicted to be major gas hydrates to be explored from the deep ocean environment, hydrogen as a fuel because the burning of hydrogen does not lead to emission of CO2, and then the geothermal energy reservoirs lying deep into the earth body. You can see here, I would just like to highlight the importance. This is the global map which shows a near uniform distribution of the distribution of gas hydrates all along the coastal line throughout the globe, and this is India. Here actually, because of the colors are faint, if you see all along the coastal line of the peninsular India, we have large amount of gas hydrates which are available. This is a typical methane gas hydrate specimen which is extracted from the submarine sediment. It is said that about a cubic meter of this methane gas hydrate releases about 160 cubic meters of gaseous methane. In view of the large potential around the peninsular India, the government of India formed a special program called as National Gas Hydrates Program, went for a first expedition in the year 2006, during which 4 different areas of the Indian Ocean were explored, including the Krishna-Godavari Basin, the Mahanadi Basin, Andaman Islands, and the Kerala coastal region. And what was discovered was that this Krishna-Godavari Basin is one of the richest marine gas hydrate accumulations. The total estimated quantity of methane gas around the Indian coastal line is of the order of almost 2,000 trillion cubic meters, a very large amount. Now, these gas hydrates have to be explored from a very large depth from the submarine environment, and the whole problem arises because these gas hydrates, they are not a stable solid. At low temperature and under high pressure, the gas hydrates, they are a stable crystalline solid, but when the pressure and temperature conditions alter, these gas hydrates become totally unstable. And therefore, to explore these gas hydrates from very deep depths, India has already exceeded a depth of almost 5.5 kilometers of drilling way back in 2013. So therefore, the safe and economical recovery of this methane gas hydrate resource is a major geoengineering challenge. The large amount of methane gas is trapped within the crystal or structure of water, forming a solid which is similar to ice, and finding sources of hydrogen from these hydrates called as methane clathrates will involve a major role of geoengineers. You know that 99% of the earth is at a temperature higher than 1000 degrees Celsius, and therefore the exploration of energy from the deep geothermal reservoirs, also its physical characterization, the mechanical characterization and exploration involves a tremendous role of geoengineering. Now this drilling process is a somewhat a complicated process, and there are many problems related to geotechnical engineering. First is that when you identify a oil field, there are many drill wells in this area, and the scientists and the engineers have to go for what we call as the geomechanical modeling of the entire oil field to define the physical properties of different layers, the mechanical properties of different layers, and how these properties alter with pressure and temperature conditions. There is a typical reaction called as a hydration reaction, which occurs in the shell formations at large depth. This hydration process or reaction is influenced by high temperature and high pressure conditions. The drilling fluid that is used for stabilizing the drill hole, there is a diffusion of free water which takes place from the drilling fluid into the shell formations due to the pressure difference in the pore water in the shell formations and the drilling fluid pressure. The drilling fluid itself has some chemical constituents which interact with the shell formation and alter the characteristics of the shell. And the shell itself, the shell formation itself, if it has got some constituents like, say for example, smectite, then it is prone to reacting with the drilling fluid, thereby altering the mechanical characteristics of the shell formations. And lastly, how to adjust the density of the drilling fluid, particularly at large depth exceeding 5 kilometers below the sea surface, in view of the varying temperature and pressure conditions at that level. And therefore, the petroleum engineers actually are largely concerned with the stability of these deep bore wells. And the stability aspect is not a problem of rock mechanics alone. It's a problem of multi-phase physics and mechanics, especially because the gas hydrates undergo phase transformation due to alteration in the pressure and temperature conditions, and it involves a coupled phenomenon of chemical-mechanical interaction. So therefore, the geotechnical engineers have a lot of role in this particular area of deep oil well drilling. Now when you go for drilling in the deep sea environment, the conventional offshore foundations do not work. So you have to go in for totally innovative foundations or totally different type of foundations. So because you have a exploration vessel at the surface of the sea, and then your seabed is at a large depth exceeding 5 kilometers, or it may be as large as even 10 kilometers. So therefore, how will you provide stability to the exploration vessel? And therefore, one of the foundation types that is thought of for stabilizing this exploration vessel is through a mooring system. You can have deep cables out of stranded steel wires, ropes, or these days they have the synthetic wire ropes, and this surface vessel, exploration vessel, can be stabilized with the help of these kind of torpedo anchors. The torpedo anchors, which are dropped from a pre-calculated height right into the seabed. Because of its own weight, it will have tendency to penetrate into the seabed, depending of course on the seabed characteristics. And then the anchoring rope will follow either a catenary profile or what is called as a taut leg mooring system, where the profile of the rope assumes a linear shape. So therefore, the anchorage capacity of such torpedo anchors in the submarine bed, that will be governed by the impact velocity of these torpedoes into the seabed, the drag coefficient or the drag that is exerted by the submarine environment, the angle of penetration of this torpedo anchor, and also the depth of penetration into the seabed. This is a conventional problem of course, anchorage, but then unless you are clear about all these parameters, it's not possible to precisely predict the anchorage capacity of the torpedo anchors. And then imagine a situation that if this is an exploration vessel which is moved into the seabed with the help of torpedo anchor, but then this foundation, it penetrates into an area where you have a slope. A sloping seabed can become unstable at that depth because of the phase transformation of the gas hydrates. And the moment the landmass becomes unstable, you can expect a landslide, and then this foundation will become totally unstable. It imparts instability to the explosion vessel. So you have problem of submarine landslides, and such a landslide, a major landslide, can also give rise to triggering of a tsunami. So again, the problems get multiplied. Apart from these problems of deep shore technology, including the exploration of the gas hydrates or methane clathrates from the deep environment, the stability of the foundations, the submarine landslides, there is another field in which I expect there would be a significant development in this particular century, and then that's the role of biotechnology in geotechnical engineering. And I anticipate two key application areas. The first one is remediation of the contaminated ground. Second one is the passive in situ improvement. In terms of applications, this will have the role of biotechnology in geotechnical engineering. We have applications in the area of soil stabilization, the stability of deep open cut excavations, even tunneling in hard rocks, passive stabilization of loose saturated sands which are susceptible to liquefaction during an earthquake, and a wider use of the underground space. Imagine that a solution of genetically engineered microorganisms plus some spatial amendments to sustain these microorganisms is injected into a sand strata throughout the depth, requiring soil improvement. You also assume that these microorganisms then produce a polymer or results into precipitation of an inorganic compound, which brings about cementation in the soil particles and also makes the soil very stiff and possibly impervious also. Then all these three major problems, you get a solution to all these three major problems of stabilization, stability of deep excavations, as well as the liquefaction of soils during earthquake. Conversely, you can apply this biotechnology to transform a hard rock also into a soft rock in the same manner, provided you are able to arrive at proper organisms and these are able to grow into the rock. So therefore, when you inject such sort of genetically engineered medium into the hard rock, it will try to convert a hard rock into a soft rock. It will decrease the cost of excavation of tunnels. It may eliminate the support system entirely, or it may drastically reduce the cost of excavation. It will also give solution to the problem of seepage into the tunnel, and it will therefore facilitate wider use of the underground space. Moreover, this biotechnology can be used also to convert the soil into a smart material. Is it possible that such a biotechnology could be developed in which a soil and a microbial system behaves as a smart material which responds to the changing conditions in the most desirable way? Just a small physical example is, let's say you have a spectacle, your specs with you, and somehow you don't know where to keep it. It may get lost, and then you will keep on searching the specs. What I can do, I can just crush the specs and put it in my pocket. And whenever I want to use it, I will just take it out, open it, and then it will regain its original shape. So therefore, these are smart materials having a certain memory, and therefore, this biotechnology can have a significant role in converting soil into a smart soil or a smart material, which the soil can be made to behave or respond to changing conditions in the most desirable way, like say for example during an earthquake, when the whole soil mass oscillates, the material is subjected to cyclic stress conditions, and the smart material knows as to how to respond to these changing oscillatory conditions and adjust it accordingly so that the liquefaction phenomenon is completely avoided. Well, friends, ladies and gentlemen, with these remarks I come to the end of this lecture, and I have got just 3 or 4 concluding remarks. The first one is, with change of times, the nature of our problems in geotechnical engineering is gradually changing, and geotechnical engineering as a discipline and also practice should therefore change. The second remark is that the old and the conventional approaches may not be adequate to deal with future technological challenges, Rather, the future challenges may have to be met with by new technological, more interdisciplinary or more multidisciplinary approaches. The third one is the widening of the role of geotechnical engineering. Geotechnical engineers, with their focus on Earth as a resource of major energy, should be ready to widen their roles and lead to solution of more challenging problems such as wider use of the underground space, more complex urban systems, discovery and recovery of new energy resources for not the next century but for the next entire millennium, like say for example the gas hydrates or the methane clathrates, exploring the role of other technologies in geotechnical engineering, like say for example biotechnology, and then dealing with some of the extreme loading conditions which are not conventionally considered. And the last major remark is that the time has come when the scope of geotechnical engineering should be broadened to the point where geotechnology, or let me call geoengineering, will draw upon several disciplines, including engineering geology and hydrogeology, seismology and geophysics, rock mechanics and rock engineering, civil engineering including the various disciplines like geotechnical structures, hydraulics as well as transportation, the deep shore engineering which forms actually the upstream area of petroleum engineering, the mining engineering, and also biotechnology, so as to yield solutions to the problems of 21st century.